Hey everyone, and welcome back for another deep dive. This time, we're tackling those early galaxies that have been shaking things up in the universe.
Yeah, they've really been
Mhm.
causing a stir.
That's right. And the James Webb Space Telescope is giving us a front row seat to all the cosmic drama.
It really is.
We're talking galaxies that are way bigger and brighter than we ever expected.
It's like we were expecting to find, a small village,
Right.
and we stumbled upon this bustling metropolis.
Exactly. Our source today is an article from scitechdaily.com, and they call it a defiance of expectations.
Oh, really?
Yeah. The article is titled Bright Galaxies of the Early Universe Defy Expectations, Sending Astronomers Back to the Drawing Board.
Wow.
So we went from this idea that, galaxy formation was this slow and steady process,
Right.
all thanks to dark matter,
Yeah.
to suddenly being like, whoa, how did these galaxies get so big so fast?
It's a big mystery.
It is. So let's rewind a bit. Before the James Webb Space Telescope came along, what was the prevailing theory of galaxy formation?
Well, the leading theory was the lambda CDM model.
Okay, lambda CDM.
Yeah. And the idea was that dark matter, this, mysterious stuff that we can't see,
Right.
it was slowly pulling matter together over billions of years.
Okay, so like a cosmic construction project.
Yeah, exactly. Little by little, galaxies would emerge. They would start faint, and then as they gather more matter, they would get brighter.
Okay, so a slow and steady process.
Yeah, exactly.
And then the James Webb Space Telescope comes along,
Yeah.
throws a wrench in that whole picture.
It really does.
It's showing us galaxies that are already huge and bright way earlier than they should be.
Way earlier than the lambda CDM model would predict.
Right. So how do we explain that?
Well, this is where things get interesting.
Okay, I'm listening.
There's an alternative theory called Modified Newtonian Dynamics, or
Yeah.
MOND for short.
MOND.
Yeah, and it's been around for a while, actually. And MOND basically says, hold on, what if gravity doesn't quite work the way we thought it did
Right.
at those massive cosmic scales?
So no dark matter needed.
That's right. MOND suggests that gravity weakens slower
Okay.
over vast distances than Newton's classic laws predict.
So a subtle tweak, but with huge implications.
Exactly.
So paint me a picture. How does this work in the early universe?
Okay, so imagine the early universe, everything's expanding.
Right.
But this slightly stronger, longer range gravity from MOD, it can pull things together much faster.
Ah, so instead of a gentle nudge, gravity's got a bit more muscle.
Exactly. And that could explain those surprisingly large and bright early galaxies that we're seeing with the James Webb Space Telescope.
And you said MOD predicted this, like before we even had the James Webb Space Telescope.
Yeah. MOND actually predicted this kind of rapid formation over 25 years ago.
Wow. Okay, so if MOND predicted this back then, why wasn't it the leading theory? What was the scientific community thinking?
Well, MOND had its proponents, but it lacked observational evidence. Okay.
And it struggled to explain certain phenomena that dark matter handled well.
Makes sense.
So the scientific community leaned towards a model that was supported by more data.
It's like, you go with the theory that has the most evidence backing it up.
Exactly.
But now with the James Webb Space Telescope showing us these early galaxies, things are getting interesting.
They really are. The JWST findings have definitely put MOND back in the spotlight.
It's like MOND is having a comeback tour.
Yeah, I could say that. Stacy McGaugh, who's an astrophysicist from Case Western Reserve University, he's been advocating for MOND for years.
Right.
He summed it up pretty well. He said, the point of science is to make predictions and then see what actually happens. And right now, MOND's predictions are aligning remarkably well with what we're seeing.
Wow. It's like the universe is saying, see? I told you so.
Yeah.
But, okay, let's say MOND is right.
Okay.
And it's modified gravity, not dark matter, that's behind these early galaxies.
Right.
Doesn't that just shake up our whole picture of the universe? It certainly does. We've spent decades building a model of the universe with dark matter as this key ingredient.
Right.
And if MOND is right, we might be looking at a cosmic recipe that needs some serious revising.
So we're talking about potentially rewriting the very foundation of our understanding of the universe.
Yeah, that's exactly what we're talking about.
That's a lot to digest.
It is.
So tell me, in simple terms, how exactly does MOND explain the early universe compared to lambda CDM?
Okay, so lambda CDM.
Or the standard model.
Yeah, it basically posits that the universe started as this smooth soup of matter and dark matter.
Okay.
And over billions of years, dark matter's gravity acted like a cosmic sculptor, gradually pulling matter into clumps that eventually became galaxies.
Okay, so a slow and steady process.
Precisely.
Like building a sandcastle one grain at a time.
Yeah, a great analogy. But MOND flips the script. It suggests that gravity itself behaves differently at cosmic scales,
Okay.
allowing for rapid galaxy formation. So imagine those initial density fluctuations in the early universe.
Okay.
Under MOND, instead of gradually smoothing out, gravity enhances them,
Okay.
leading to a rapid collapse of matter and the formation of large galaxies in a relatively short amount of time.
So it's more like gravity's playing cosmic Jenga,
Aha, I like that.
pulling out blocks and letting structures collapse quickly.
Yeah. And this difference in how gravity acts is the key distinction between how MOND explains the early universe
Yeah.
compared to the standard lambda CDM model.
Okay.
It challenges the idea that we need dark matter to explain the large-scale structure of the universe.
Okay, I'm starting to get the big picture. So if MOND is correct, and it really is modified gravity driving galaxy formation, what does that mean for dark matter? Does it just disappear?
That's the million-dollar question.
Yeah.
And it's a topic that deserves its own deep dive.
Well, we've got plenty more to talk about.
Oh, we do.
But before we go down that rabbit hole, let's just take a moment to appreciate how these new observations from the James Webb Space Telescope are really pushing us to reconsider some of our most fundamental assumptions about the universe.
I agree. It's an exciting time for cosmology.
Yeah, it's pretty mind-blowing. So we have this incredible tension between MOND and lambda CDM.
Right.
Both are trying to explain the universe, but they're doing it with very different ingredients.
It's a fascinating scientific debate, and the James Webb Space Telescope is adding fuel to the fire.
It really is.
And what's so exciting is that this tension is driving us to ask deeper questions,
Right.
to design new experiments, and to look at the universe with fresh eyes.
It's a reminder that science is a process of continuous discovery and refinement.
Absolutely.
There's always more to learn, and the universe is always full of surprises.
I couldn't agree more. And as we delve further into the MOND versus dark matter debate, it's important to remember it's not about choosing sides or declaring a winner.
Right.
It's about expanding our understanding of the universe and appreciating the complexity and elegance of the laws that govern it.
Well said. This deep dive has definitely opened my eyes to a whole new way of thinking about the universe.
I'm glad to hear that.
But there's still so much to unpack. We've got to explore how MOND handles other cosmic phenomena, like gravitational lensing,
Right.
and delve into the search for a unified theory of gravity that could bridge the gap between MOND and general relativity.
Indeed, there's a lot more to explore.
There is.
But before we journey further into the cosmic unknown, let's take a moment to reflect on what we've learned so far.
Okay.
We've seen how the James Webb Space Telescope is challenging our assumptions about the early universe, how MOND offers a compelling alternative to dark matter, and how this scientific debate is pushing us towards a deeper understanding of the cosmos.
It's a reminder that the universe is full of mysteries, and the pursuit of knowledge is an ongoing adventure.
Well said. Now, are you ready to dive deeper into the MOND versus dark matter debate?
Absolutely. Let's unravel this cosmic enigma together. All right, so we've established that MOND offers a pretty compelling explanation for those early bright galaxies.
It does.
But you mentioned earlier that it has some trouble explaining other cosmic phenomena like gravitational lensing. Can you elaborate on that?
Sure. So gravitational lensing, it's basically when the gravity of a massive object,
Okay.
like a galaxy cluster, it bends the light coming from objects behind it.
So it's like looking through a giant cosmic magnifying glass.
Yeah, I guess so.
So we're seeing these distorted images of distant galaxies because their light is being warped by the gravity of something in front of them.
Exactly. And dark matter because of its gravitational influence.
Right.
It's thought to play a big role in this lensing effect.
Okay, so how does MOND handle this? Does it just ignore gravitational lensing?
Not quite. MOND does predict some degree of lensing,
Okay.
but it's often not enough to match the observations.
So there's a discrepancy there.
Yeah, this discrepancy is one of the main challenges for MOND.
Ah, so it's like MOND's got a bit of a blind spot when it comes to gravitational lensing.
You could say that, but remember, science is all about refining our understanding.
Right.
MOND proponents are tackling this challenge head-on. Some are tweaking the original MOND equations, adding extra parameters, or modifying how gravity behaves at different scales.
So it's like MOND is getting a tune-up to address these inconsistencies.
Exactly. Some of these modifications might seem a bit like adding bells and whistles,
Right.
but others are based on deeper theoretical considerations. Trying to create a more comprehensive theory that can explain both galaxy formation and gravitational lensing.
So instead of throwing out MOND altogether,
Yeah.
scientists are trying to make it more robust, more able to explain a wider range of observations.
That's the spirit of scientific inquiry. And it's not just about fixing a MOND to fit the data.
Okay.
Some physicists are exploring even bolder ideas, trying to merge MOND with Einstein's theory of general relativity.
Wow. Combining MOND and general relativity. That sounds like a pretty ambitious goal.
It is, but if we could find a unified theory that incorporates both, it'd be a major breakthrough.
Right.
It would mean we've found a framework that can explain both the large-scale structure of the universe and the behavior of gravity at all scales.
Okay, so we've got these efforts to refine MOND and even potentially unify it with general relativity.
Right.
What about the flip side? Are there any attempts to modify dark matter theories to better explain the JWST observations?
That's a great question, and the answer is yes. While the JWST observations have provided a boost for MOND,
Right.
they've also prompted some dark matter proponents to re-examine their models.
So it's not just MOND that's evolving, dark matter theories are also adapting in light of new evidence.
Exactly. Some researchers are exploring the possibility of different types of dark matter,
Okay.
with different properties and interactions that might better explain the early galaxy formation we're seeing with the JWST.
So it's not a simple case of MOND versus dark matter.
Yeah.
It's more like this complex interplay of ideas with both sides adapting and evolving as we gather more data.
That's a great way to put it. The JWST observations have thrown a wrench into our understanding of the early universe.
They have.
But they've also injected a healthy dose of excitement and creativity into the field of cosmology.
It's like the universe is challenging us to think bigger, to be more imaginative, and to keep pushing the boundaries of what we know.
Precisely. And that's what makes science so captivating.
It does.
It's not a static body of knowledge. It's a dynamic process of exploration and discovery.
Well, this deep dive has certainly been a journey of exploration. We've gone from those unexpectedly bright galaxies to the intricacies of MOND to the ongoing quest for a unified theory of gravity.
We have.
But okay, let's talk about the implications.
Okay.
If MOND is right, how does that change our understanding of the universe beyond just explaining these early galaxies?
That's where things get really interesting. Remember, MOND challenges one of the fundamental assumptions of modern cosmology, the existence of dark matter.
Right.
If MOND is the correct description of gravity,
Yeah.
it means we might have been attributing certain cosmic phenomena to dark matter, when in reality it was modified gravity all along.
So those vast halos of dark matter that we thought surrounded galaxies might not even be there?
That's one of the radical implications of MOD. Instead of dark matter driving the formation of galaxies and influencing their rotation,
Right.
it suggests that gravity, acting differently than we currently understand, is the dominant force.
Okay, but if dark matter isn't holding galaxies together, what's stopping them from flying apart?
MOD provides an answer to that. Remember, it suggests that gravity weakens at a slower rate over vast distances.
Right.
This means that even though galaxies are rotating at high speeds,
Yeah.
the enhanced gravitational pull from the MOND framework is enough to keep them bound together.
So instead of needing this invisible dark matter to provide extra gravity, MOND tweaks the way gravity itself behaves to achieve the same effect.
Exactly. It's a paradigm shift in our understanding of gravity and its role in the universe.
That's huge. But it's not just about galaxies, is it? What other cosmic mysteries could MOND potentially solve?
Well, for starters, MOND might offer insights into the expansion of the universe.
Okay.
The standard model relies on dark energy to explain why the universe's expansion is accelerating. But some end-and-death theorists believe that modified gravity could account for this acceleration without the need for dark energy.
So instead of adding another mysterious ingredient to the cosmic recipe, MOND tries to explain the observed acceleration using the modified behavior of gravity itself.
That's the idea. It's a more economical explanation in a way.
I see. But doesn't MOND also have some problems explaining the cosmic microwave background radiation, the afterglow of the Big Bang?
That's another area where MOND faces challenges.
Okay.
The standard model, with its inclusion of dark matter and dark energy,
Right.
it fits the observed patterns in the cosmic microwave background very well.
Yeah.
MOD, in its original form, struggles to reproduce these patterns.
So it's not a perfect fit yet.
No theory is. But that's what makes science exciting.
It does.
We're constantly testing our ideas, refining our models, and searching for a more complete understanding of the universe.
This deep dive has really highlighted how MOND is shaking things up in cosmology.
It is.
It's offering alternative explanations for some of the biggest mysteries in the universe. Yeah.
And it's pushing us to rethink some of our most fundamental assumptions.
It's an exciting time to be exploring the cosmos. We have these new observations from the James Webb Space Telescope,
Right.
these intriguing theoretical frameworks like MOND, and this vibrant scientific community constantly pushing the boundaries of knowledge.
I'm definitely feeling inspired to learn more, but before we wrap up this part of our deep dive,
Yeah.
I'm curious, are there any other implications of MOND that we haven't touched on yet? Anything that might surprise our listeners?
Well, one of the fascinating things about MOD
Yeah.
is that it suggests a connection between the smallest and largest scales in the universe.
Okay.
Remember how MOD modifies gravity at vast cosmic distances?
Right.
Well, some physicists believe that this modification might also have implications for the behavior of gravity at the quantum level.
So the realm of atoms and subatomic particles?
Exactly.
So MOND could potentially bridge the gap between the very big and the
Yeah.
very small.
That's the idea. It's a tantalizing possibility and one that researchers are actively exploring. Wow.
Imagine if we could find a single framework that could explain the behavior of gravity from the scale of galaxies down to the scale of quarks.
Right?
It would be a revolutionary achievement in physics.
That's pretty mind-blowing. So MOND is not just about explaining galaxy formation.
Right.
It's potentially a key to unlocking a deeper understanding of gravity itself.
Exactly. And that's why it's so important to keep an open mind, to explore all the possibilities, and to let the evidence guide us as we delve deeper into the mysteries of the universe.
Well said. This deep dive has been an incredible journey so far. We've explored MOND's strengths, its challenges, and its mind-boggling implications.
We have.
But I have a feeling there's still more to uncover.
You're right. We still need to explore how scientists are actively testing MOND.
Yeah.
What experiments are being conducted, and what future observations might help us finally determine whether MOND or dark matter provides the most accurate description of the universe.
Sounds like we have a lot more ground to cover.
We do. But before we delve further into these fascinating topics, let's take a moment to recap what we've learned so far and prepare for the next leg of our cosmic adventure.
Okay, so we've been on quite the ride through the cosmos.
We have.
We've seen how MOND challenges our assumptions about dark matter and offers a different perspective on gravity's role in the universe.
Yeah, it really shakes things up.
But the big question remains, how do we actually test these theories?
Right.
How do we figure out whether MOND or dark matter is the right way to understand the universe?
Well, that's the heart of the scientific method, isn't it?
It is.
We need to put these theories to the test.
Right.
Compare their predictions with observations and see which one comes out on top.
So what kind of tests are we talking about?
Okay.
What observations can help settle this cosmic debate?
Well, the James Webb Space Telescope, with its ability to peer into the early universe, it's already providing valuable data.
It is.
And if it continues to find large, bright galaxies at those early epochs,
Right.
it would further support MOND's predictions of rapid galaxy formation.
So more early galaxies would be a point in MOND's favor.
Precisely.
Yeah.
But it's not just about the number of galaxies.
Okay.
Astronomers are also meticulously studying the properties of these galaxies, their shapes, their rotation curves, their chemical compositions.
Okay.
By comparing these detailed observations with the predictions of both MOND and dark matter models,
Right.
we can get a better sense of which theory provides a more accurate description.
So it's like a cosmic detective story,
Yeah,
with each new clue helping us piece together the puzzle of the universe.
exactly. And we're not just relying on telescopes.
Okay.
There are also experiments being conducted here on Earth that can shed light on the nature of dark matter.
Wait, we can study dark matter in a lab?
Yeah.
How does that work?
Well, the idea is to directly detect dark matter particles.
Okay.
We know that dark matter interacts very weakly with ordinary matter.
Right.
But if we build sensitive enough detectors,
Yeah.
we might be able to catch a glimpse of these elusive particles.
So imagine we have these super sensitive detectors
Right.
shielded from all other particles and radiation.
Exactly.
And if we see a tiny blip, a signal that can't be explained by anything else, it could be a dark matter particle.
That's the hope.
Huh.
And there are several experiments around the world trying to do just that.
That's incredible. So we're looking for evidence of dark matter in the depths of space and in the heart of our labs?
Yes.
It's a multi-pronged approach to solving this cosmic mystery.
Exactly. And it's not just about proving one theory right and the other wrong.
Okay.
The real goal is to expand our understanding of the universe,
Right.
whether it's through confirming the existence of dark matter or revealing the intricacies of modified gravity.
It's a reminder that science is a process of discovery, not a battle between competing ideologies.
Well said. And sometimes the most exciting discoveries come from the places we least expect.
Right.
Remember when MOND was first proposed? It was considered a fringe idea.
It was.
But now, thanks to new observations and theoretical advancements, it's a serious contender in our understanding of the universe.
It's a reminder to never underestimate the power of a good idea, even if it goes against the mainstream.
Absolutely. And who knows what other revolutionary ideas are out there just waiting to be discovered.
Okay, so we have telescopes peering into the early universe,
Yeah.
experiments hunting for dark matter particles,
Right.
and theorists working tirelessly to refine our models.
That's right.
What else can we do to push the boundaries of our understanding?
Well, one exciting avenue is computer simulations.
Okay.
We can create virtual universes on supercomputers,
Right.
input the laws of physics,
Okay.
and see how these simulated universes evolve over time.
So we can run different scenarios, some with dark matter, some with MOND, and compare the results to what we observe in the real universe.
Exactly. And these simulations are becoming increasingly sophisticated,
Okay.
allowing us to model galaxy formation, large-scale structure, and even the cosmic microwave background radiation with incredible detail.
It's like having a cosmic laboratory at our fingertips.
Indeed. And as our computing power grows, these simulations will become even more powerful tools for testing our theories and pushing the boundaries of our knowledge.
So we have observations, experiments, and simulations all working together to help us unravel the mysteries of the universe.
That's right.
It's a truly remarkable time to be a cosmologist.
It is. And the best part is that we're only just beginning to scratch the surface.
Right.
There's so much more to discover, so many questions still unanswered.
That's both exciting and humbling, isn't it?
Absolutely. It's a reminder that the universe is vast and complex,
It is.
and our understanding of it is constantly evolving.
Right.
But with every new discovery, with every new insight, we get a little closer to comprehending the grand cosmic tapestry.
This deep dive has taken us on quite a journey.
It has.
We've explored the James Webb Space Telescope's groundbreaking observations, delved into the intricacies of MOND, and contemplated the profound implications of modified gravity.
And along the way, we've encountered a universe full of wonder, mystery, and endless possibilities for exploration.
So what's the takeaway for our listeners, those intrepid explorers who've joined us on this cosmic adventure?
Here's what I would say. Embrace the unknown.
Yeah.
Challenge your assumptions and never stop asking questions.
that.
The universe is full of secrets waiting to be uncovered.
It is.
And the pursuit of knowledge is a journey that never ends.
Well said. And as we continue to explore the cosmos, who knows what mind-blowing discoveries await us? Perhaps MOND will revolutionize our understanding of gravity, or maybe dark matter will reveal itself in unexpected ways.
It's exciting to think about.
It is. Whatever the future holds, one thing is certain: the universe will continue to amaze and inspire us.
I completely agree.
Well, that brings us to the end of another deep dive.
It does.
Thanks for joining us on this cosmic adventure.
It was my pleasure.
And remember to keep those deep dive requests coming. We'll be back soon to explore more fascinating corners of the universe.
Until next time.
Keep looking up.